Hello and welcome. This video provides some technical background behind the common mode rejection ratio test, which is applicable to all types of ECG equipment. This particular test is one of the more complicated tests in the standard, both for the theory and the application. This video covers the theory, standards, the design of the Whale-Tech Cmrr test box, and also some practical testing issues. A separate video covers the actual test method. Common mode rejection ratio is a typical specification for any equipment with a differential voltage measurement, including multimeters, differential amplifiers, and of course ECG equipment. In a perfect world, a differential input would not respond to any common mode voltage. In practice, there is a small effect. Because the effect is small, the specification is normally declared in decibels or dB. A value of 60 dB means the common mode voltage is reduced by a factor of 1000. Every 20 dB is a factor of 10. In this example, there is a differential voltage of 1 volt and a common mode voltage of 100 volts. If the meter has a specification of 60 dB, it would result in a display of 1.1 volts instead of 1 volts RMS. In ECG standards, the typical requirement is 1 millivolt peak-to-peak indication with 10 volts RMS applied. This calculates to around 89 dB Cmrr as shown. It turns out that for Cmrr, an imbalance in the impedance in each lead makes the result much worse. Multimeters typically specify a 1 kilo ohm imbalance. The ECG standards use a 51K resistor in parallel with 47 nanofarads capacitance to represent connection to the body. This imbalance has a large effect on the test result. ECG equipment uses a variety of strategies to handle Cmrr, including an isolated circuit, right leg drive, capacitance to ground, and filtering. However, the standard requires that special mains filters are turned off for the test. This is to make sure that the hardware alone can really handle the test. Otherwise, the ECG trace can get distorted. There are 3 IEC standards for ECG equipment. IEC 60601-2-25 for diagnostic, -2-27 for monitoring, and -2-47 for ambulatory or Holter ECGs. In the US there are similar standards and of course a range of standards around the world for national regulations. For now, let's use -2-25 as a base for the tests and discuss the variations later on. As already mentioned, the basic requirement is that when 10 volts RMS is applied, the equipment should indicate less than 10 millimeters with a normal sensitivity of 10 millimeters per millivolt. But the standard adds some complications. The first is that the lead electrode being tested must have the series impedance of 51K and 47 nanofarads. This creates the imbalance and causes a much larger indication than the balance condition. This impedance also appears in the right leg, although the effect of this is usually negligible. The diagram in the standard shows an impedance with a switch in each electrode, but the text indicates that all switches are shorted except for one. Next, a series DC offset of 300 millivolts is added. This generally has no effect on the result, but is anyhow required by the standard. Finally, instead of applying the voltage directly, the standard requires us to start with 20 volts RMS and create the 10 volts through a divider made up of 2 100 picofarad capacitors. This creates an equivalent circuit of 10 volts source with a series 200 picofarads. This actually helps the equipment to pass, as the equipment can load down the voltage during the test. A typical ECG input has around 100 to 300 picofarads to earth, which brings the actual test voltage down to around 4 to 7 volts RMS. Because of the high impedance of the 100 picofarad divider, the test setup is very sensitive to external noise. For this reason, the standard requires a double shield construction with the internal shield floating at the common mode voltage, or 10 volts, and the external shield grounded. The double shield has a variable capacitance, so an adjustable capacitor is used to set up the 10 volts RMS before the equipment under test is connected. Finally, to note that the latest IEC standards require all mains frequencies to be tested, typically 50 and 60 Hz. Fortunately, the latest versions of -2-25 and -2-27 are fully harmonized for the test circuit and test method. Also, -2-47 has the same test method except for the test voltage and frequency. However, the older version of -2-47 and the AMI standards have an opposite approach to create the imbalance. The IEC version has the imbalance in one lead only, while the AMI version has the impedance in each lead except one. The IEC version generally has higher results, but only in the leads tested, while the AMI version has lower results, but in all leads. In IEC 60601-2-47, the test voltage and frequency is different to other standards. This is due to the equipment being worn on the body. There are some practical issues with the setup in the standard, which are solved by some of the features in the WhaleTech Cmrr box. First, the output of most function generators is limited to 7 volts RMS. The Cmrr box includes a transformer to step up to 20 volts as required by the standard. Second is that at mains frequency, 100 picofarad capacitors are very high impedance. This means that it's very difficult to directly measure the 10 volts. For this, the Cmrr box includes a special 1000-to-1 divider, so that an output of 10 volts can be measured indirectly as 10 millivolts. Finally, instead of using many switches to create the imbalance, the engineer simply moves each lead electrode to the imbalance terminal one by one. The opposite configuration in the old -2-47 and the AMI standards is implemented using the general purpose ECG breakout box. This breakout box accesses the alternate network inside the Cmrr box. The box also includes the 300 mV DC offset powered by a small coin cell battery, the double shield, and an adjustable capacitor as required by the standard. Noise can be a problem in testing. In particular, if the noise is significant and the test frequency is similar to the environment, beating can occur, which appears as an unstable test result, slowly changing with time. Noise reducing methods are shown in the operation manual. Note that for the ground shield to be effective, a minimum thickness of 1 mm is recommended. Cables should be kept over the ground plate, and noise sources such as AC cables and power supplies should be removed from the test area. As previously mentioned, the ECG can load down the voltage. This includes the stray capacitance from the cables. It is recommended to bundle the cable over the ground plate, but not to wrap it tightly in aluminium foil. After setting up, always check for expected test results. With the function generator off, we expect to see less than 1 mm on the ECG record, even in the imbalance condition. With the function generator on, we expect to see 2 to 7 mm on the ECG record in the leads that are affected by the lead electrode that has the imbalance. If these kind of results don't appear, check for noise and connections. So that's it. We've covered the theory behind common mode rejection ratio, the requirements in the standards, the design of the WhaleTech test equipment, and some of the testing issues. If you have any further questions, feel free to contact WhaleTech using the details shown. Thanks for your time.